And this is Monday. Let me see. So we will keep discussing the things about the fixed point method, and also the another new method is called Newton's methods. And so let's get back to what we have. Let me see. Do we have the things here? Not really. But let's see. No, this is the fixed point methods, and we just briefly mentioned this last time. So first we have the fixed point method, and then we say this method depends on the functions we choose, the g function, and we have one example. So now we translate the this is the root finding problem, and then it's finding the root of this function, and actually we can rewrite this problem into several format, several fixed point format, and then A, B, C, D, E. And if you take a look at the simulations we have in this picture, and then you find out that the A and B format does not work because it's divergent. This one is undefined because this is the negative number square root. And for the C, D, and E, and then it works, and then the problem, the methods converge to a number, and then that is the root of the equation there. For the E expressions, and then we get a very fast convergence result, and then it converges to the root of the function, root of the equations with 4 iterations. And so from these examples, and then we are wondering how can we choose that function g such that it has the convergent result. And this is the fixed point theorem, and all the assumptions is quite similar to the fixed point problems theorem, that is theorem 2.3. It's about the uniqueness and existence. But here, for this fixed point theorem, we have the same assumption. G is continuous, and then the range of the G is the subset of the domain of G. And we also assume that the derivative exists on the interval and is bounded by a K. And this constant K is smaller than 1. And with all these assumptions on the G, and for any, this is very important, you will see there's some things different later, the assumptions. So for the fixed point theorem, we have for any initial guess, P0 in the interval AB, the sequence defined by this, and then converge to the unique fixed point P. And we have some things very important here. This is for any initial guess, and then later on, you will find out that for the method we are going to learn, that is the Newton's method. The Newton's method, we have restrictions on the initial guess here. And this is the fixed point theorem. And I'm going to show you the proof of this theorem. And later on, I'm going to give you one corollary. It's about the convergence rate of these methods. And now I'm going to show you the proof for this theorem because it's quite interesting. And then you have already seen this in the final exams before, the final exams of 104B, if you are taking the 104B with me. And so let's see. So from the theorems, so first, from the theorem 2.3, and then it's already has the uniqueness and the existence. Implies that a unique fixed point exists in the interval AB with the GP equals to P. So there's another thing that we need to say here. this is the uniqueness and existence of the fixed point from the assumptions about the G function. And the next things we need to assure that make sure that the sequence Pn here is well defined. And this is because since the G maps the AB to itself, hence the sequence is well defined. The sequence Pn n equals to 0 to infinity is well defined. This is because if you take a look at what we have here, is that so every time you get a Pn minus 1, and then it's belonging to the domain. This is the domain of the G, right? And once you define the Pn with the G function, and then because the domain, the range of the function is a subset of the AB, or the mapping result, Pn is belonging to the domain again. So this one, so because the Pn is also belonging to the domain, so which means that we can define the next iteration because this is belonging to the domain of the G. So this is why the sequence is well defined, because the range of the function is also the domain, is the subset of the domain of the G. And then when we do the mapping, and then the result is also in the domain of the G, so that we can apply the G functions to the Pn again. And this is why we have a sequence well defined here. So this is something we need to state before we go to the convergence result. So next, we are going to make use the criterion on the conditions on the G, that is the G point. The derivatives, the BAM of the derivative is smaller than or equals to the K. And using the fact that the G, this is the derivative of the function is smaller than or equals to K. And we are going to use the mean value theorem here. Mean value theorem. And you will see that the mean value theorem, the Taylor expansions, is used throughout the 104A, 104B, and 104C. And now we are going to use the mean value theorem here to get the convergence results. We have for all the n, for each n here, we have, so first of all, we are going to investigate the convergence result. So we are going to calculate the errors between the numbers Pn and the true solution. So the difference between this is the true solution and this is the approximation. And we are going to calculate the difference of them before, and with the generation through, so we generate the Pn in this way. Pn equals to G, and then G function supply on the Pn minus 1. So which means that, and I'm going to replace this. So here we replace the Pn with the G Pn minus 1. And what about the true solution? And then what does the true solution mean? This is the solution of the fixed point problem. And then so P satisfy the P equals to GP. this is the approximations, and then by the approximations through, and then this is the Pn equals to Pg, and then apply to the Pn minus 1. So now I'm going to replace the P with the Gp, and now you have the function apply on the point Pn minus 1, and the G function apply on the at the point P. And for this one, we are going to apply the mean value theorem, and then there is just a point that is the Cn, Cn, and then it's the G point derivative evaluate at the Cn, and then times the function times the value, the difference between the Pn minus 1 and P. And this is the mean value theorem. From this part to this part, we apply the mean value theorem here. And then for the Cn, there's a range for the Cn here. So this one is the mean value theorem. And also for the Cn, we know that the Cn should be between the Pn minus 1. I'm not sure the order of the Pn minus 1 or P and P, but it should be the interval between the Pn or the P and then Pn minus 1. Maybe the Pn minus 1 is bigger, maybe the Pn minus 1 is smaller. And so Cn should be in this interval. And now, because, but one thing we are sure, we can make sure that is that, so this possible two interval is a subset of the AB. And this is something we can make sure the Cn is inside the interval AB. So next we have, so we are going to take the absolute values to the each side, each item, and then we have the G prime Cn, and then Pn minus 1 P, and this one should be equal sign here, the absolute value. We just take the absolute value to each item here. And then for this one, the first one is bounded by K. This is because we have the assumptions on the deductive bound. This is the bound for deductive, so we have the K here for this deductive. And we just leave the Pn minus 1 and then P here. This is the first step. And this is pretty the same as the things we have done for the final exams last time. And this is the first step. And we have to do more things to get to the convergence result. And first, we get to these things, and then we call it as the inequality 1. And let us apply the inequality 1 inductively, and then we got this. So Pn and then minus P. So this is the inequality 1, and then Pn minus 1 and then minus P. And if we apply this inequality, and then let's say we change the n to n minus 1, which means that we replace the n with n minus 1. And then here, the n minus 1 is replaced with the n minus 2. So that we have another inequality here. And then we can apply to this item. And we get this. So for this one, replace the n with the n minus 1 in the inequality and the inequality in the inequality 1, and then we just replace the n with the n minus 1, and then we can have So now the K, we just copy the K from the previous item here. And then for the Pn minus 1 minus P is bounded by the K and Pn minus 2 and then minus P. And this is because this part is smaller than this part. And we are going to apply this being equality 1 to this part, and then we get the bound for this part as well, and then we will apply the inequality inductively to the P0 minus P. So here, this is just a K square. This one is just K square. And so if we keep apply the inequality to these items, and then at the end of the day, and then we got this Pn minus P difference, the absolute value of the Pn minus P, and then we have this one is smaller than the Kn, and then P0, and then minus P. And then the P0 is just the initial gas. This one is the initial gas. And then this one is the true solution. This one is a true solution. So now what we have here, we have some things, we already have the convergence results. So this is a convergence result because from the assumptions, we also have a restrictions on the K constant. The K constant is a number, a positive number, but it's smaller than 1. And so now we have the N. So this is the also one restrictions on the constant K. It's positive, but it's smaller than 1. And so this one, we have the limit, the K to the N. This is the power term, and then but the N, the power is tends to infinity, and because the K is less than 1, for example, this is 0.01, and then if you let the N, we do the power N here, and then letting the N tends to infinity, and it is always said this item is going to 0. So for the K, which is smaller than 1, and then the power N here is tending to infinity, and then we have the limit, it equals to 0. This is something we learned from the calculus class. Any questions here? So before, because this one, so let's take the limit of the previous inequality, N tends to infinity, Pn minus P. And then on the right-hand side, we are also taking the N tends to infinity, and that is Kn, and then P0, and then minus P. And because the limit N tends to infinity for the K to the power N equals 0, so on the right-hand side, we have equals to 0. And this means that, so we can get to the conclusion, hence, and then Pn, and then N equals 0 infinity converge to the P. Any questions here? Any questions? It's about the convergence. It's just about the convergence itself. It's just telling you if we get this sequence of the number, and then it's just convergence, but it doesn't tell you anything about the convergence rate. But the convergence rate for the fixed point methods is quite important. It's also related to the, if we talk about the Newton's method later on, and then the Newton's method is some things related to this fixed point methods. Any questions before we move on? The proof. So let's go or give you some overview of this things. So first we need to state that the existence in Linux, and then this sequence is well defined, and then we are using the fact of the G prime concept. G prime, that this is the derivative, the bound of the derivative, and the mean value of the mean value theorems, and then to derive the bound for the Pn minus P. And then, so with this inequality one, we apply the inequality one inductively, and then so we have the Pn minus P. This difference here is bounded by the Kn, k to the power n, and then the initial error. This is the initial error. This is the initial gas. This is true solution, and this part is just the initial error. And with the assumptions on the k constants smaller than 1, and then we can get that this Pn sequence is convergent to P. This is the overview of the proof. And if you don't have any questions, and then we are going to get the corollary, and then the corollary is quite important. It's about the convergence rate of the fixed point methods. So this is the convergence rate of the fixed point method. And for this part, we have, so we are going to make the statement first. This is the corollary, and then which means that it's based on the theorem 2.4. So all the things should satisfy the assumptions on the assumptions in the theorems 2.4. Then the bounds for the error, or you can say it's just something related to the convergence rate. Bounds for the errors are given by this. So this is the bounds for the error, and this is the error, Pn minus P. Pn is the approximation, P is the true solution, and it's smaller than or equals to the k to the power of n, and then taking the maximums, P0 and then minus A, and then B minus P0. And this is the maximums of the initial gas to the left endpoint, and then the right sign is the right endpoint to the initial gas. So we take the maximums of them, and then that's the things. And the next is the Pn minus P is some things about array convergence here, and then it's Kn, and then 1 minus K, and then P1 minus P0. And then for all the n is bigger than or equals to 1. So let's see how to get to this corollary. Actually, we already got some things here, something similar to here. So why don't we use this to say this is the convergence rate or the bound of the error? Because we don't know these two solutions yet, so we cannot use this criterion to bound the errors to take a look at the actual results, and then how well we did in the actual computations. So we are going to use this indicator instead, and then that is a P0 minus A, and then we know the left endpoint, we know the initial gas, and then so we can have the bound for the error. And this is just the theoretical result, but we don't know the true solutions are not in most of the cases. And so now let's derive this from based on the theoretical results on the error part. But this one is more usable because we know the initial guess, we know the left-hand board. It's just very simple, just one step from this part to this part. And so let's see. So here, there's the proof here. A lot of time, I want to mention again about this. So when you do the error bounds, and then you will see that it's not useful to get such a bound in your actual calculations, where you have the true solutions on the right-hand side. And because most of the time we don't know the true solutions. So here, a lot of the time you need some something you know on the right-hand side to bound your errors. And then that's the convergence results. And now let's get back to here. So this is something the same things you have in the 104B, or later on in our class we have Newton's methods or others, ODE algorithm. And then on the right hand side, for the convergence rate results, we should use something we already know, not the solutions, the true solutions informations in the right hand side bound. So now let us prove this convergence rate. And from the theorems 2.4 proof, we have the Pn minus P is bounded by the Kn, and the Pn minus P, P is the true solutions, right? But now P is 0. So that's the things. So here we have the interval A and B, and maybe the true solution is here, is a P. Maybe the P0 is here, as the initial guess. And so for the interval here, for the difference here, is just a P0 minus P. And if you take a look at this interval, and it's definitely smaller than the bigger interval we have here, the P0 to the B. So this is the B minus. This part represent the B minus the P0. And but this part, the blue part here, and then it represents the P0 minus P. And so it's always that this part is smaller than this part. And another case is that, so there's another case, it could be the P0 is getting closer to the B here, and but maybe the P is here. Once again, we could have the same situation. The P0P is less than the B minus P0, but the B minus P0 is also smaller than the bigger interval here. And this is another case. And this is another case here. This is always smaller than the things we have here. But here, there's another case, that is the A, B here. And then, but the P0 is getting closer to the B, but the P might be here. But in this case, you will also get the P minus P0 is less than an interval here is the P0 minus A. So this is the P0 minus A interval, and then this is just the P0 minus P interval, the length of the P0 P interval. but this one, the length of this interval is less than the P0 minus A. So that's what we have here. You have another case, might be the other cases here. But all the cases indicate that we have the P0 minus P is interval, the length of the interval here is smaller than the maximums of the P0 minus A. That is the initial guess, the distance between the initial guess to the left endpoint, and then the distance to the right endpoint. And then taking the maximum between these two distance, and this two, the maximum of these two distance always bound this P0 minus P. That is the initial guess to the two solutions. So this is what we have here for the first one. So for the second one, we are going to use the first iterations results to bound the approximations result here. This is the first iteration result. This is the initial guess, and then how can we achieve this convergence rate here? And we are going to prove this. Once again, here we need some mean value here to help us to prove the results we want. So next, we are focused on proving this result here. And this one is the first iterations result. The first iterations result, and then this one is an initial guess. And from our results is also based on the theorems 2.4. And so first, let's get to here. So this is the first part. The second part. We are going to prove this. So first, for the Pn plus 1 minus Pn. And we got, so first we know that this one is the G Pn minus 1, and then minus the G Pn minus 2. This is N, and then N minus 1. And this is because the generation rule for the fixed point methods. And next, we already got, so this is something similar to what we have in the proof of the theorem 2.4. And we get the mean value theorem here. And then this mean value theorem, we get the derivative of the function. And then but the derivative function can be bounded by K. So we have something similar here, but we just use the K to bound the result here. K and then Pm minus Pn minus 1. So in case that you cannot understand this part, and then I'm going to write something here. Is equals to, this is the mean value theorem, and then this one is the because something is depend on the interval we have. And let's say this is the G prime kasi and then Pm minus 1. And because this part is smaller than or equals to K, so that we have this part. This is the inequality, and then this part is the mean value theorem. And we would keep apply this inequality inductively. This is similar to what we have in the proof of the theorem 2.4. And then we keep doing the inductions here. And this is K squared, because if we apply the inequality here again, that is the K times the K, and then Pm minus 1, and then minus Pm minus 2. And this is because if you have the first inequality here, and then you replace the N with N minus 1, and you will have, this is N minus 1, this is the Pn, and then this is smaller than or equals to K, and then this one is Pm minus 1, and then minus Pn minus 2. And this is exactly what we have here. This part is smaller than the things inside the parentheses here. You just need to replace the n plus 1 with n here with the in the first inequality here. So we would go to apply this inequality inductively, and then at the end of the day, you will have this one is smaller than or equals to Kn, and then P, this is P2, P1, and then P0. Any question here? So for this part, we just excuse me. So for this part, from this part to this part, we just use the first inequality we have here, and then but change the index here, change the n to the n minus 1, and then we keep apply this inequality inductively, and then we get to this result. So this is the first part, and then we have the Pn plus 1 minus Pn, and then it's smaller than n equals to the Kn, k to the power of n, and then P1 minus P0. And then next, we are going to estimate something more. It's something similar to the it's just the distance between 2 points. It's something similar to what we have in the Lipschitz continuous conditions. It's any arbitrary point in the sequence. And then we bound it. We want to bound it. And so for this one, we are going to use the technique, and then it's just some things we have. It's called telescoping. So we are going to use the telescope, and then it could expand, and then it could collapse. And then so this is the telescoping technique. And then we add some tons there, and then subtract some down. It equals to the Pm minus 1, and then plus the Pm minus 1. You can see I just add some things in between, and then subtract at the same time, and then plus Pn plus 1. And the last two items should be like this. Three items. And then minus the Pn minus plus 1, and then plus the Pn plus 1, and then minus Pn. All the things in between is subtracting and then adding again, subtract and add it again. So it doesn't change the result. But now, so here we are going to have one inequality here. That is the Pm minus 1, and then plus the Pm minus 1 minus the Pm minus 2, and then all the way to Pn plus 1 minus Pn. So now you have the difference between the neighborhood. This one is the difference of the neighborhood, but here you can take arbitrary two numbers from the sequence, and then you can estimate the difference between them. And so now this part with the telescoping technique, and then we translate the things into, this is the difference of two arbitrary items. And then, but here, all the things in this expansion here is the neighborhood items. So here we have, for these items, we can use the results we have here. For examples, for this one, we have, this is a k to the power, so that this is the n, right? This is the k to the power n, and then this n is depending on the Pn index here. So for this one, we have the k index, and then it should be the k index, and then to the k to the power of the n minus 1. And so this one, it should be the BAM here. We have, it should be the k to the m minus 1, and then p1, and then minus p0. This is because the power m minus 1 here is depending on the m minus 1 here. And we would do the same things for the remaining item, km minus 2, p1 minus p0. This one is because we have the m minus 2 here. This index is m minus 2. And we would do the same things, apply the first inequality, the neighborhood difference to the last one, and then it's k to the power of n, and then p1 minus p0. This is the difference between the first iteration result and the initial guess. So at the end of the day, let's get to so the kn is the smallest, the n is the smallest power we have, and then this is the n, and then we are going to extract the common items here. So that is p1 minus p0. And so for the first one, we have the 1 coefficient k squared coefficients, and the km minus n minus 1 coefficients. If you take a look at here, the kn times 1 is corresponding to this one, kn times the k item, it should be the same in front of this one. And the kn times the k to the power of m minus n minus 1 is corresponding to this item. So it's going to, so from here, from the left to the right, is corresponding to the item from the last item to the first item. And this is the inequality here. We pick any two arbitrary items from the sequence, and then we estimate the difference between them. And with this result, we can go to the next step. So we are going to estimate the solution, the error, right? So next, p minus pn, and this is what we want to estimate. And we are going to get the pm minus pn here. This is the solutions, the things we have in the previous steps. We estimate the two items between the difference between two arbitrary items in the sequence. But now I'm going to take the limit m tends to infinity. And there's an equal sign here because pm is also one item in the sequence. And then so if we take the m to the infinity, and we have already got that the sequence is converging to p. So which means that if we take the limit here, m tends to infinity, this is going to p, and that's what we have here on the left hand side, p minus pn. And this is what we have on the left hand side. And on the right hand side, we are going to use the difference for two arbitrary items above here. We have the inequality result here. So we have it's smaller than or equals to, let me see. I should have something here. It should be the limit m tends to infinity, and I just copy them all the things we have from the above, and then doing the second sum, I equals to 0, and then m minus 1, and this is a k to the order of I. And but there's one more thing here. So there's a smaller than or equal sign here, and then that is the kn. There's nothing changing about the n because we are taking the limit to the infinity. And for this one, is smaller than or equals to the sigma sums to the infinity, the index. So this is the things. And there's one more things here. You will see we are almost there. This one is the Kn, and then the error here, and then divided by the 1 minus K. And if you compare what we already have, and then you will see that, so we already got the things on the top, and then this one should be equals to the 1 over K. So if you compare to what we are going to prove, and then this one should equals to 1 over K. And actually you have this because the 0, this is the K is a positive number, and then it's smaller than 1, and hence the geometry, this is a geometry series, and then this one from the calculus class knowledge, and then you already know that this geometry series is converging to 1 over 1 minus K. Does it make sense? So at the end of the day, so hence we can conclude that the P minus Pn, and then it's smaller than or equals to the Kn, and then divided by the 1 over K, and then P1 minus P0. Any question here? So we collect, from the very beginning, we just estimate the neighborhood difference, and then and seconds, and then we do the difference between the any arbitrary items. We do this. This is because we are going to estimate this error here, and then we let the P to be the limit of the Pn. And so that we can estimate this part, and then taking the limit m to infinity. And by using the results above, and then we have this results here. And then for this part, and then we are going to we are going to use the we use the geometry series results, and then this is 1 over 1 minus K. And this converge because the K is smaller than 1. And that's all the things about the proof. And then now you have the convergence results, 2 parts. And then the first part is just the Kn, and then you are using the initial guess and then the interval points, the left endpoint and then the right endpoint. And this is the first version of the convergence results, and then there's another version of the convergence results. And then you are going to use the first iteration result here to bound your errors. And then this is the second part of the convergence result. And any questions right so far? No questions? The proof is long, it's lengthy, but it's quite interesting because it's using the inductive technique here. And you will see this again and again in the other classes. If you take the functional analysis, and then you will see this proof again. And this is all the things we want to mention today. And then I'm going to release the homework today because we finished all the discussions on the fixed point methods. And hopefully we will get something similar to this proof, and then you will enjoy the proof here. Okay, class is over. If you have some question or some personal concerns, and then you can come over to discuss